Hey everybody, Bait here, and this is a pretty important video. We are going to be proving the chain rule here. So we know that ddx, right, we need to find ddx of f of g of x. And so what we can do here is use the limit definition of the derivative. I actually proved this in another video in this series, so make sure to watch that. So this will then be the limit as delta x, or I could say, h approaches 0, of f of g of x plus h minus f of g of x all over h. And now I kind of want to do some weird algebraic manipulation here. It kind of seems weird, like I would never think about really doing this, but the person who created this proof did, and so we're just going to follow it. But mathematically, this is correct, and you should know why this is, right? We're just multiplying this by g of x plus h minus g of x in both the numerator and the denominator. And so now we get this limit here. And so we get, or what I'm actually going to do here is I'm actually going to switch the denominators. So I'm going to make it here as f of g of x plus h minus f of g of x all over g of x plus h minus g of x. And then here we'll have g of x plus h minus g of x all over h. Okay, what I did here is I just flipped the denominators. And now using one of our properties of limits here, I can split this limit up as a product of two limits. So we can have h approaches 0 of f of g of x plus h minus f of g of x all over g of x plus h minus g of x times the limit as h approaches 0 of g of x plus h minus g of x all over h. And hopefully you recognize this. We're just literally using the limit definition on g of x. So this should be g prime of x, or g of x by dx. Well, I'm just going to use Lagrange's notation here. I'm not going to use Leibniz's notation. So we have g prime of x here, but what are we going to do about this guy here? So this is kind of an interesting case. Okay, how are we going to deal with this kind of composition of functions? Well, I'm just going to let this denominator here, I'm going to say, like, we'll let g of x plus h minus g of x equal to, I don't know, c, okay? So firstly, if we think about c here, as h approaches 0, c must also approach 0, right? Because if h approaches 0 here, we'll be left with a g of x minus g of x, right? Which will be 0 as well. So c would also have to be approaching 0. Right, so that's a true statement. And also we can just rearrange this as, right, g of x plus c is the same as g of x plus h. We'll keep that in the back of our head. So now rewriting this in terms of our c here, we can write the limit as c approaches 0, because if h approaches 0, then c will also approach 0, of f of, and then g of x plus h. Right, g of x plus h is just g of x plus c. G of x plus c minus f of g of x. And then this will be all over then our c, right? Because c is just g of x plus h minus g of x. And then this will be then times g prime of x. And so now, hopefully you kind of see this already, but I'm going to make it even easier for you to follow. We're going to let, we're going to let a equal to g of x here. So then we can rewrite this as the limit as c approaches 0 of f of a plus c minus f of a all over c times g prime of x. And this is actually, right, this is again limit definition, but instead of at x, at some value x, it is at some value a, right? So it's the derivative at some value a. So this is just going to be here, again, if you're confused, c approaches 0, right? This still, even though c approaches 0, it doesn't matter, it's just a variable. This is in the form of the limit definition, but it's at a point, it's at c, it's at a. And so really, this is just going to be f prime of a times g prime of x. But then what is a? Well, a is just g of x. So this will then be f prime of g of x times g prime of x. So we can say, therefore, d dx of f of g of x is the same as f prime of g of x times g prime of x. I thought this was a pretty good proof. Well, I mean, the person who created it. I don't know if my skill of conveying this was really that great. It's kind of sloppy, but hopefully this kind of makes sense. I thought this was the most straightforward proof of the chain rule that I've seen so far. So I want to share it with you guys. Cool.